more colligative properties of solutions, because the whole chapter's about that, right? We were talking about a solution that was made of 2 or more volatile elements. Now let's talk about what happens if you put something that's non-volatile into a volatile solvent. So what you have here is a little terrarium set up so that the liquids are separated, but the vapor is not separated. Since this is pure water, it tries to go into equilibrium with what's up here. The seawater tries to go into equilibrium with the atmosphere above it, but since they share the atmosphere has to be the same above them. So what's the net result? Well, if you took this and ran it long enough, what would happen would be that the water keeps trying to provide more water vapor up here. Meanwhile, the seawater is saying, oh no, that's too much. That's too much. Let's pull more of the water vapor back down into the liquid. And ultimately you end up with an empty side and a side that now has been diluted. So we say that the presence of the solute particles in the seawater lowers the vapor pressure of the water, because according to Raoult's law, the mole fraction of water is smaller than it would be in pure water. In fact, we can write that down. We could say, hey, let's have Raoult's law. The pressure above the solution is the mole fraction of the solvent, and the pressure that would normally be above the solvent. And then we have chi for what is dissolved in it, the solute, right? And the pressure of the solute. But in this case, we're talking about a situation where this part is equal to 0 because it's not volatile. So if that's 0, then the only thing left is this. The pressure above the solution is the mole fraction of the solvent, and the pressure that would normally be above the solvent reduces to a very simple form then. And this is what we've written here. So the vapor pressure of the volatile solvent is lowered because the non-volatile solute is contributing no pressure. The more non-volatile solute particles, it will lower the vapor pressure of the solution because this chi goes down. The more of these solutes there are, the less chi of the solvent is. And it doesn't matter what that identity of the solute is as long as it's non-volatile, because then it's just going to say, oh, my vapor pressure is 0, so everything that was out here that was added to this, nope, it's just 0. That solute is lowering the mole fraction of the solvent. And so this is very important. The more of the solute particles. So if you have a situation where you have an ionic that is breaking into extra pieces, then each one of those is going to help decrease how much chi of solvent is, because they're creating their own chi, which is taking away from the whole business of the chi's having to add up to 1. This is our phase diagram, and it's more complicated than it used to be. I mean, it was complicated enough before, right? We had a line here that separated solids from liquids. We had a curve here that separated liquids from gases. And then we had a line that, well, sort of a line, a curve between the solids and the gases. And we had a triple point where you could see all three at the same time, which is kind of cool to think of, seeing liquid and solid and gas of the same substance all in existence at the same time. It's rare enough to have 2 of them having a phase change, but having all 3 show up, well, that's cool, okay? But if we go back to what we started our chapter with, we talked about boiling point elevation, and that was here at 1 atmosphere. We were talking about, oh, I'm going to throw in a bunch of a solute, and it's going to have a boiling point elevation. The temperature is going to go up. So down here, here's your delta TB. There's your boiling point of the aqueous solution, as opposed to the normal boiling point, which is what 1 atmosphere tells you normal, right? So we had this where it got boop over to here. And we also had freezing point depression over here. If we had something in the solution instead of the liquid being pure, we had a freezing point depression, so the temperature went down. The freezing point of the solution was lower than the freezing point of the pure water. Well, we could do all of this again at lower atmospheric pressures. We could just lower the pressure and do it, and we would find that we would still have some sort of boiling point elevation and freezing point depression. And doing that, we can create two new curves, changing where the phase change is between solid and liquid, and changing where the phase change is between liquid and gas. So we end up with these being almost completely parallel to where the originals were. And when they meet, you have a new triple point of the solution, and it will happen at a lower temperature and a lower pressure. So this whole thing is trying to get the idea across that part of why this occurs, the boiling point elevation and freezing point depression, is Raoult's law. And we can sort of see how that was fit together now. And it's all because they're all colligative properties.